I mean, apparently sucks.
Yeah, it's either my situation, whether I stand the heat in my apartment or stand the banging in the office.
Yeah, no, I was coming in before it started every day, but once it started, I stopped coming in because it was giving me a headache.
Hi, David. Hi, Aaron. Hi, Amir. Hi, Yulun.
Hello.
Amir?
Yeah.
Are you going to show slides yourself, or you want me to flip them?
I prepare it myself.
Okay. Hey, Johan.
Hi, Dr. Kevin. How's it going?
Doing good. Nice seeing you connected. Hi, Fatima.
Hi.
Hi, Fatima.
Let's maybe wait for a couple of minutes if more attendees will join.
Yeah, I know that Dr. Xia also will join the meeting. I see that almost all of you are working from home. Just Johan and I come back to the offices.
I'm in Dunbar.
Yeah, well, I guess with construction, you know how they have that large.
Oh, yeah.
It's like our office is literally 50 feet from that.
Oh, okay, good.
Yeah, it's really annoying. I just looked up the schedule. It's scheduled to end on the 26th.
Okay. Yeah, fortunately, we are far enough from that construction site, so will not affect our offices.
Have you seen the images from webcam? Or if those who are coming to the campus do not need it. I cannot find it right now, but some of the colleagues were sharing the image, how the I don't know if this chat room is transmitting the text well.
It's just a big gray rectangle.
Yeah, it I don't know why it goes. It's not very smart activity to retype slash. I'm doing it probably first time in life, typing the YouTube address by hand.
Do you prefer this platform to the Zoom, Dr. Smith?
Well, we do not need a license for that, and there is a active support.
Okay.
Active support. Indeed, Zoom has a little bit higher quality, I admit it. So it's just a little entertainment while we are waiting for more people to appear. So we do not need to go to the office. We can watch everything.
Okay.
That looks like it's almost right over my head.
Yeah. So I'm going to maybe send a reminder.
Maybe Dr. Xia is in different time zone actually for the season because he's online. Let me give him a message.
Sarah Gazanafari. Oh, it's a new person I never met. Hello, Sarah. Let's get acquainted.
Sorry, my dad.
Oh, okay, okay.
New student in our group.
Oh.
PhD student actually.
Okay, okay, yeah.
Hi, Dr.
Hi, Sarah. Thank you for joining and supporting Almiro.
Actually, that Xia invite all group of students to join.
Very good, very good. Yeah, it's a good idea.
I don't know if it's okay with you.
Absolutely, absolutely.
Okay, good. Oh.
Oh, so I think everyone is here. So let me announce. It is a joint meeting between research groups in engineering and chemistry and biochemistry. So collaboration meeting with group of Professor Wenjie Xia, and today's presentation will be by okay, so here by Amirhadi Alesadi. So he took class in computational chemistry and did very interesting research project there. So he is looking on electronic and optical properties of the specific class of materials, and one specific example of this class of material, conjugated polymers that have some semiconducting properties while being completely organic and flexible, which makes them important candidates for like making bendable computers and maybe some medical applications that can contact with human body. And there will be several aspects that Amir will cover, and it may serve as inspiration to members of both groups from both mechanical properties and electronic. So the material that Amir is going to talk about is periodic with explicit momentum distribution, which has some properties of solids. It has some ability to conduct electricity, especially if the charge is injected, which is important property to compare to experiment. And potentially one can explore change of the structure upon injection of the charge or excitation, which relates to so-called polarons in flexible materials. So all attendees are invited to make notes and share them later with Amir, or if he is okay, to stop the speaker and ask questions during the talk, or better after the talk. So the main goal of this meeting for Amir is to collect feedback on what can be improved or what should be emphasized. So with this, I would like to give floor to Amir. Please start sharing your screen.
Sure. Can you see my screen?
Yes.
So you can see the first page of the slide, right?
And yes, first side, and I can see your laser analog of laser pointer.
Okay. So yeah, thank you, Dr. Tinin, to give me this time. I'm happy to join your meeting, group meeting. This is my learning process, and I want to start with this sentence from the Nobel Prize winner that nobody can understand fully the quantum. So for me, for sure, I cannot learn it in this quick time. I just tried some few aspects of this kind of material. So today, as Dr. Kinin said, we want to focus on this PDPP-based conjugate polymer. So the motivation of this study was that recently we published a paper on this kind of polymer. We focus mainly on the gas transition temperature and the mechanical properties of this kind of polymer. So as you can see in this top left figure, this is a monomer of this kind of polymer. So the backbone of this branch polymer consists of some tyrosine group and also pyridine group, and the R represents the side chain structure. Side chain is alkyl group. So for that paper, we consider several side chain lengths, but for today's study, to save the computational resources, we just choose the shortest side chain length. So C6 and C8 means that there is 6 carbon in each branch, so totally there is 2 branch. For that study, we use a post-year molecular dynamic simulation also to mimic the essential structural feature of that study. So today, for this study, to do some quantum modeling, we model a dimer to build the periodic model. So as you can see, the shortest side chain length is chosen to represent this model, and this is the computational model that is collected from VMD. The system is expert in the Z direction, as you can see, and this is also from a view from another plan. So first, this is the optimal geometry of the model, the geometry set of the system, and in the coming study, we want to check some results from the band gap as absorption, etc., and other kind of the results that you can see. So first, the density of estates is shown here. The difference between HOMO and LUMO, actually occupied and unoccupied orbital, is observed around 0. Sorry?
Would you allow to ask questions as we go?
Yeah, I'm okay.
Okay, so can you give names for the building blocks of the polymers? And if you're not sure, maybe we can guess them by collective brainstorming. Like there is a thiophene group, there are alkyl side chains, and what else is there?
Okay, so this ring, we call them thiophene group. The carbon ring, one carbon is replaced by a sulfur. This group, if I'm not wrong, this is a pyridine group that oxidates with the oxygen. And these side chains, they are alkyl group. So C6H13 means that there is 6 carbon in each chain, and the carbon, the valence shell is full by the adding some hydrogen and bonding with the hydrogen. And if I think these 3 groups, this is again thiophene group, this is the pyridine group, and each chain is the alkyl group that the length is 6, including 6 carbon and 8 carbon. And the side chain in the both sides is the same. So anything else, Dr. Kirin, you think?
I'm fine. Let's check if anyone in the meeting wants to add correction, or if it sounds fine for everyone.
Sure.
So no one is objecting, which means it is correct. David, would you like to accept this answer, or you have some corrections?
I'm okay with it.
Okay, thank you.
So
I'm not sure it's pyridine, but I'm not sure enough to say that it's not either.
I think, yeah, pyridine is a hexagonal ring, yeah, if I'm not wrong, but I call it pyridine, so I didn't find another name, but I will double check if
okay.
We can use another name.
Okay, sorry for interrupting, please keep going.
That's fine, that's fine. So first of all, we plot the density of state to see the band gap of the system. So for the semiconductor, there is a different range for band gap, maybe from 0.1 maybe to 2.8 or 3. I saw different reported values. But for this model, with the current system, the band gap is observed around 0.9 electron volt. So, and HOMO and LUMO also are labeled in the figure. So after density of a state, we can check the absorption spectra. This absorption spectra can give us some important information. So as it is mentioned here, each peak is corresponding to a pair of orbitals, one occupied orbital and another one unoccupied orbital. So actually for each pair of orbitals, show the energy, the transition energy that needed to promote some electron from occupied orbitals to unoccupied. So we can use the oscillator experiment to plot these models, and yeah, if somebody has this information, for instance, the tallest peak means that this pair of occupied and unoccupied orbital has the highest potential to be promoted, to be excited. Maybe that can be happened by the service comment in the in-car if somebody is interested in. So let's take a look through the transition energy. This is the transition energy of the system, and also the wavelength that's represented here. This actually the orbital that are labeled here with the label HOMO-1 to LUMO +1 with A, B, C, and D. For sure, the shortest, the smallest value of transition energy is for promoting the electron from B to C, from HOMO to LUMO. This first peak represented B and C, actually going from unoccupied to occupied. Also, after the second peak represented from if we want to have electron from A to C and also from B to D. If if I'm doing something wrong, please correct me. And the last one, I just showed the four frontier orbitals here. And last one is when electrons are from A to D, this unoccupied orbital. Also, if we check the wavelength, actually the energy of the emitted wavelength can be correlated with the energy electron transition from occupied to unoccupied orbitals. So the first peak, the shortest, the smallest transition energy is corresponded to the biggest wavelength here. So for instance, for 0.9 transition energy between the HOMO and LUMO, actually between P and C, is corresponding to around 1400 wavelength. Also, other orbitals are shown here, for instance, A to C, B to D, or A to B. So, any question until here?
Yes.
I'm afraid if I can answer your question.
No. You did answer it in. Maybe you can refer to the answer of the question on one of the following slides. The lowest transition here is 1.8 or 1400 nanometers. How does this result stays the same or changes if you use different functional?
Actually, we have the result. For instance, if we use some hybrid function calculation, the result will be different. If you let me know, I will show you in the coming slides. We have some results for that.
Okay, you will show it later, but does the gap becomes wider or shorter if you use different functional?
I use besides this, I use the HSC06, the hybrid function, and the gap would be larger.
Okay,
this,
very good. Very good. Thank you.
Okay, thank you for your question. The another one, we want to check the momentum dispersion of the system. So first, I want to introduce the effective mass. As you know, the particle effective mass is the mass that I just read the sentence. Sorry, that seems particle mass that seems to have when they respond to a force for interacting with the other particle. Also, for the electron mass and also pole mass, this mass is represented in a relative state, and usually it's divided by the m0, that is the mass of electron, or we call them the rest mass of an electron, that is, the value is reported here. This is the dimensionless momentum distribution for the band energies. The band energy are normalized by subtracting from the average of HOMO and LUMO. So the band structure, the E, actually can be locally approximated by the following functions. So the momentum distribution that are obtained here for four frontier orbitals can be approximated to find the MH and ME. So here K is the x-axis. So this H for H bar is the Planck coefficient divided by 2p, and E0 means that the value of the K at the 0, actually the value of energy, the band energy at the 0. So to do this calculation, first let me go to this slide. To find the value at the 0 momentum, I fit cubic order polynomial to the value, for instance, here, the value of the orbital 314, the LUMO plus 1, just to get the value of energy at the zero momentum. Then one can obtain ME and MH for different orbitals. As you can see from this table, the value of MH and ME are reported. So if we divide them with the M0, that value is reported here. We can find this relative value of the mass. And if again, I'm wrong, please correct me because I'm not pretty familiar with this field. But as you can see, the relative value of the MH are higher than the ME. So I can interpret that this system should be whole conductor. Please correct me if you accept or disagree with this statement. Also, from this equation, one can obtain the ME and MH, as I told, as the definition of the effective mass. This is the point that I'm curious about. The mass of the system, the mass of the particle is maybe a function of the force or momentum of the system. According to this value, each system should have a different mass, maybe by changing the momentum. So usually we expect to have a constant mass, but here we plot the mass for frontier orbitals by this equation. As you can see, for HUMO and LUMO, after starting after passing the initial value of the K, the momentum, we have a constant value for the mass. But for a little for HUMO -1, orbital 311, and more for LUMO +1, 314. We can see that for each value, actually for each value of the momentum, we have a different mass. And especially the mass is 0. I checked some references. Mass, the negative mass is possible. It means that the sign of the mass is different from the mass of the matter. But I'm curious if Dr. Killing can interpret this is something wrong by my calculation, or no. For instance, why the mass of the system here is different, and at least is not constant.
It is artifact of having not enough grid points of momentum near zero. So you have this energy difference in denominator, and it's just artifact. If one takes more points and do not look at the exact zero of momentum, it should be fixed. So your results do not look problematic. It looks reasonable.
Okay.
But if you allow, I'll ask a question. Can I?
Okay.
Would you please interpret the effective mass in the following sense? How does effective mass influences, the value of effective mass influences the conductivity? On the simple example, like which value of effective mass gives better conductivity? Heavy electron or light electron? Like large effective mass or small effective mass? When the conductivity will be higher?
I think, I don't know if you right, but I sense that when we have a lower mass, the electron should have a higher mobility, so may end it in higher conductivity.
Other different opinions in the among attendees of the meeting. So let's flip one slide back.
Here.
Okay, and look on the green line for LUMO. just we just look on it by eyes.
For the LUMO, okay?
That starts at plus 0.5 at momentum equals 0.
Okay.
So this line is approximated as parabola, and effective mass is inverse curvature of this parabola. So the shallow parabola will mean that there are a lot of states accessible to excite with minimalistic amount of energy. So shallow parabola and heavy mass, which will mean that one can apply infinitesimal amount of energy to accelerate particle to high values. While if the mass will be small, then the parabola will be steep, and one would need to apply more and more energy to ramp up the particle and give it more velocity. So heavier particle, larger mass is better for conductivity. And
conductivity, okay.
Okay. Sorry for interrupting.
So,
please keep going.
No, I'm learning from you here. So here, MH for the FUMO is heavier than the ME because of this, because this whole conductive first, is it right or no?
Mm-hmm. So whole is
the whole conductive system are have better performance in conductivity than the electroconductor systems. As you mentioned, we can conclude this or not?
Yes, you are right. So whole has heavier effective mass, not drastically, but it is heavier. So it will take less effort to ramp up, to accelerate the whole, and the whole conductivity will be a little bit more efficient than electron conductivity.
Okay, thank you. So any question on this here?
Okay, I think you can keep going.
Okay, sure. So the other point that in the coming slide we want to check the charge density of these 4 frontier orbitals. First, I start with HOMO -1 orbital and 311. You can see that the maximum charge density appears around the oxidized hydrogen group, but this actually localized charge is not uniformly distributed. So this localized state maybe is not conductive. If we go forward to HOMO, the orbital 312, you can see charge density appeared on the pyridine group, oxidized pyridine group, but for each pyridine group, there is a reasonable amount of the charge density. So the charge through the backbone is not localized anymore. So this delocalized state means that this orbital state is conductive. So the other point is interesting for me, but for sure not surprising for you. This alkyl group didn't show any contribution in the charge here. We found that this system highly affects the glass transition of the glassy polymer and also its mechanical properties, but maybe the citric group does not affect the charge of this system. The next orbital state is LUMO 313, and again, as you can see from this plot, the highest charge appeared on the hydrogen group, but again, there is a good amount of charge for the hydrogen group, and this system, this delocalized conjugated state, can be converted. And the last state for the charge density is LUMO plus 1. And this, again, the maximum charge appears on the carbon of the pyridine group. For each pyridine group, again, there is some charge distribution. It's not delocalized, but also is not a complete localized. So it may be considered as a partially charged conductive. So these are the initial results that we got from this project. Dr. Kilin provided me 6 steps that to improve the results. As for instance, he mentioned if we use another function, how the band gap would be different. So I just copy and paste Dr. Kilin comments. For step number 1, recompute the single post-Beyond state using the HSE 6 functional and get DOS and spectrum. And Dr. Kilin predicted the gap be larger. As you can see, yes, the gap show a larger value, 1.2. Actually, this HSE function incorporates a portion of I just want to read the exact sentence, action from the article theory, and also incorporate this with some approximation and empirical results. So the results, this is a more expensive calculation, but the results should be more accurate than the previous results that we checked. So for this using HSE06 in intercoil, we observe a almost 1.2 electron volt band gap. And the absorption also is represented here. You can see again from LUMO -1 to LUMO +1. If we check the transition energy for the system, again, the lowest transition energy appears for B2C, from HOMO to LUMO, unoccupied to occupied orbitals. And for the other transition energy for going from different unoccupied orbitals to from occupied orbital to unoccupied orbital also is shown here. And again, if we check the wavelength, for sure, the shortest, the smallest transition energy is correlated to the longest wavelength. And as Dr. Kilin suggested, I checked some experimental results for this kind of polymer. Here we can see the results that are provided for different molecular weight. You can see that the band gap value are reported around 1.3 here. And I'm not sure, Dr. Kilin, this is the maximum, this is the wavelength of the band gap that is reported here, between 800 and 815 almost nanometer.
Sometimes the maximum of the absorption does not coincide from literal gap if the gap state is not the brightest.
Okay, thank you. Also, I checked some other references. This value for another reference, for instance, this polymer PDPP, they call them PPT, is reported around 1.33. And also the maximum absorption from the experimental results from different references is reported around 800 nanometers. So, Dr. Kilin, I have a question from you. It's a general question. For DFT calculation, usually researchers try to find the exact value near the experimental results or no. Maybe it's similar to molecular dynamics. They want to try to understand the general behavior of the system.
Both. If one cannot achieve agreement with experiment, then there is a poor man argument that we are exploring general trends. But if it is possible to achieve agreement, it would be really great. And in the light of what you are showing, one may try to put to place the spectra, experimental spectra and computed spectra on the same axis, and if they coincide, then it would be a great report of success. If they do not coincide, it will be a guidance towards additional effort to improve, either by new calculations or just by suggesting what can be done in achieve better convergence. So,
Okay.
so yes, please. Let's ask the audience if any suggestions can be made for practical steps towards improving the agreement with experiment. So if we look on the current slide and a couple of slides before, we have experimental and computed spectra, and there are 3 points of difference, of divergence. First, the computed gap, even with hybrid functional, is more redshifted. The lowest peak in absorption spectrum is redshifted compared to lowest peak in experiment. So here it is like 1.05 or 1030 nanometers, and on experiment it is like 900 nanometers. So it is the first thing. Second, in the spectrum that is computed, the lowest transitions are very sparse. There is a individual peak like B to C, A to C, and there is nothing between them. While on the experiment, there is a continuous band, which is probably composed of many transitions. So it is discrepancy number 2. And what is number 3? I don't remember. Maybe there are only 2. So anyone wants to suggest any tricks or approaches how to fix these two things?
Well, hi, Dimitri.
Yes.
Hi. So
Yes,
I think,
Kevin.
yeah, these are very good, but I think it's key to compare the simulation results with the experiments. Even though there might be some discrepancy which happen a lot, right? From the computation perspective, we want to understand this difference. That's the most important thing. So here, regarding these 2 discrepancies between the simulation and experiments, right? 2 points mentioned by Dr. Keeling. I think we should be careful that when we make the comparison, whether we compare apple to apple or apple to orange, right? Mm-hmm. So it seems to me that the current results you show, is from the experiment. It's mainly for the melt or bulk system, right? It's not for individual conjugated partner chain. Is that correct?
Yes.
So
you didn't read in detail, but I think so, yeah.
Yeah, so that's my question. Whether that bot behavior will be different, from the single chain. So, for example, the band gap or absorbance spectrum, those kind of things. Whether if you look at the one single individual chain, right, versus a bot, multiple chain put together, right? Yeah. You look at the band gap and.
So you are absolutely correct, and if one considers distribution of chains, even if they do not interact, in these soft materials, each thread is a little bit different, and if one makes summation over several of those, it will be so-called inhomogeneous distribution. So the line, spectral line of the same nature will be a little red or blue shifted in each individual thread, and this will provide broadening and partially make the spectrum more dense and continuous. Yes, this may be an yep.
So another thing is that for the band gap, you see the experimental result is a little bit larger, right, than the simulation. Is that correct, Amir? So is that reasonable if we look at the block behavior because of this inhomogeneous, random oriented chain distribution, whether that will increase the band gap or lower the band gap? That is the
typically this inhomogeneous distribution lowers the gap. So yes, so this inhomogeneous distribution is a good observation, and we should take it into account. But it could be not alone. There could be few more corrections that may bring to a excellent or at least better correspondence. I'm not telling that we need to do anything else, but at least we need to pave the way. Which steps?
We want to rationalize the results.
Exactly. Yes. Exactly.
Explain that. So, for example, my question is that for example, if you have a multiple chain put together as shown in the experiment, and because of this charge transfer across chain, right, through the pi stacking in this type of polymer, and whether that will create some inefficiency to enlarge the band gap compared to the single chain.
This is a very bright idea about charge transfer states, but the mechanism may be a little bit special. So charge transfer states do not contribute oscillator strength. They are dark. And through this charge transfer mechanism, the lowest transitions in the multiple chains will be darker. And then the next lowest will stay bright. And then it will, quench absorption and emission of the lowest transition. So it may, this mechanism may bring the peak towards higher value. Yes.
Okay. So another thing is that if you look at these two plots, right, you can see that for shorter chain, the left figure there's the lower microwaves, right, which means the chain is shorter in average, right? The right one is larger, is much larger, longer chain length. So you can see that. To me, the spectrum shift towards the right, right? Am I correct? Right? If you look at the peak, right? The peak value.
Yes, shorter chain shifts to red shift. Yes.
Yeah. So that could be something we want to maybe think about. The chain length, for example.
If one decides to do no more calculations and just try to publish it, then this comments could be a really good discussion section of trying to rationalize what is happening. But I would like to check with Dr. Han, with Yulun, and with Dr. Fatima on their opinions. What else can be potentially made in order to bring better coincidence, better correspondence between this computation and experiment.
I guess I have two suggestions.
Yes, please.
The first one is about the simulation cell. I'm thinking maybe you can just increase the length of your cell. Maybe you can get a better band gap. The second one is about the solvent.
Okay.
Maybe add explicit solvent or explicit solvent into your simulations. Maybe you can increase the gap.
Okay. Yep. Thank you. So one can either make several strands, or include the solvent through this WASP sol, right? Not explicit solvent, but polarization continuous medium. Okay. Yes,
Mhm.
it's great. Yeah. Thank you. Thank you. And Fatima, do you have another suggestions, specifically how to fill the gap between first and second transitions?
I'm not sure if my opinion will be right. So is it okay to calculate the absorption spectra for different K points and then combine them?
Yes.
Is
Yes.
that making it sense?
Right now, Amir shows absorption. Yes, it is absolutely perfect comment. So right now, Amir is showing absorption spectrum computed only at gamma point, right? And if one would include intermediate different values of momentum and include them in absorption spectrum, it will be not discrete lines, but it will be continuous set of lines immediately filling this gap and at least qualitatively coming to agreement with experiment. Yes. Amir, would you please show the...
Yeah, I have a quick comment here.
Please.
Dr. Xia mentioned that this current band gap is different. So here we have just a donor periodic model, that's maybe single chain,
Mm-hmm.
to the bulk behavior. So I read few papers about this topic. This polymer in the melt state or maybe below the gas transition shows some crystalline region and also amorphous region in the bulk behavior or in the tensile behavior. So through the crystalline region, for sure, this backbone makes some crystal region, so it shows higher conductivity. And people are trying if they can increase this crystal region and decrease the amorphous region. This will affect the P stacking and interchain conductivity of the system. So I'm not sure. This, for instance, Dr. Kinney, if we put another dimer behind this, the current model, the band gap could be larger or smaller. Can you emphasize this again?
Highly likely it will become smaller.
Okay, but I think finding the bulk behavior band gap with the DFT because the computational resources are very limited. I don't know.
No. We are not as limited. It will be very natural step to build a cell with densely packed several strands. And it seems possible. Just if one does it at once, it will be too many things. So we may decide to focus on the simplest model to clarify all issues and create a foundation from which one can go to more details. Amir, would you please bring slide with lucky number 13?
1-3 or
1-3.
This one?
Yes. So can you do annotation? Can you draw on your screen?
Sure.
So would you please, yes, where you are now, start arrow and connect by vertical line, go from green to red.
In this area, you mean?
Yes, yes.
So what are you looking for?
No, from HOMO to LUMO, not from LUMO to LUMO plus 1, but from HOMO to LUMO.
From HOMO for red to green, right?
Mm-hmm. Okay, so this is the lowest transition that is computed in the absorption spectrum, right? So the momentum assumed to be zero, so-called gamma point.
Okay, sure.
But please do a copy of this vertical line from HOMO to LUMO at the value of momentum equals to 0.1.
Value of moment.
Just make another arrow going from red to green, from HOMO to LUMO, at different value of momentum. Just make a little offset to the right.
Oh, it doesn't look.
It's fine. It's fine. And now please make few more lines, few more arrows in between. Okay, and enough. So the transition that you are drawing right now, it will be HOMO to LUMO. It will be on your nomenclature still transition B to C, right?
Yes.
But the length of arrows is different depending on the value of momentum. And if one includes transitions at each value of momentum, it will be not single line at a given energy range, but it will be multiple lines. It will create additional broadening and additional shape of the spectrum. And then we may miss the band gap, but qualitatively the spectrum is expected to be much closer to the one on experiment. So it is a suggestion of Dr. Fatima to put she suggested to put these multiple lines that Amir has drawn right now, to include transitions at different values of momentum. And this is expected to substantially improve.
Okay, that was your comment that you mentioned to tell us the key points actually momentum. Okay, I got it. I got no.
I have a question here.
Yes.
So Amir considered 16K points. So do we need to plot absorption spectra for the 16K points or 4K points go there?
Well, if it is easier and quicker to do for 4K points, it will be better than for 1. But larger number will give more precision and better correspondence to experiment.
Yeah, I can do that. Okay.
Okay, and so we can address both of challenges, making the spectrum more continuous through suggestion of Fatima with multiple K points, and we may try to blue shift the gap by including the polarized continuum medium by solvent, as Dr. Han, as Yulun has suggested. Even if we do not do it practically right now, we can mention these two opportunities. So we do know how to achieve better convergence with experiment. And then the step number 3 would be to simulate densely packed several strands that interact to each other and will make model even more realistic and qualitatively in agreement with experiment. Whew. Okay, Amir, sorry for interrupting you for so long time. If there are no more questions at this slide, please continue your story.
Okay, I appreciate your comments. So, each comment is, yeah, we saw that there is a bigger band gap for HSE hybrid functional in conform. Again, the band gap with transition from B to C is appeared the lowest transition energy. And again, if you got the wavelength for this system, you can see that the lowest transition energy corresponding to the biggest wavelength, around 1050, for instance. And this was reported value around 0.3 for this value. The step number 2, Dr. Killian suggested to, I don't know if it is doping the system, increasing the number of electrons in coil from, because the model already have 624 electrons. So we increase in step number 2, and 2 electrons and increase the number of electrons to 624. The interesting point for me, that was the strange. So the HOMO, we shift HOMO from 312 to 313 here. We do not see, we cannot see a band gap anymore here between the HOMO and LUMO. It means that we increase the actually conductivity of the system by increasing the band gap. This is one interesting point from this plot. Another one is that it's not a band gap, but I don't know, we can call it a sub gap or something like that. Sub gap is appeared in the previous, actually between HOMO and LUMO of the original model, electron neutral model. So that was the interesting point. So, and if we plot again the spectrum and from transition energy and the wavelength, that we can see this negatively charged system needs less energy to promote from electrons from occupied orbitals to unoccupied orbitals. So, Dr. Chile, I have a question, or also you or other audience can have questions. Why when we dump the system, when we increase the number of electrons here, we still have the gap in this? And yes, we don't have band gap. We literally we can say that this system is more conductive. But what is the role of this sub gap in the system? Can you please clarify it?
If we will all learn from Dr. Fatima, if we will use multiple K points, then there will be almost no subgap. So this subgap between 313 and 314 is at gamma point. If you explore more K points, it will be much, the gap will be much less.
Fatima, any comment?
So I understand that working, and again, you already did a lot of calculations, and maybe at this point it's better to keep results as they are and just add comments. But generally, I realize personally how much pressure on brain is to change mindset and think about K points. And there is a shortcut to avoid dealing with K points at all, completely. So by replicating and making the simulation cell longer, twice as longer means including 2 K points instead of 1. Making it 4 times longer means including 4 K points instead of 1. So if one needs 16 K points, one can still work in gamma point, but just make a huge simulation cell. And then all results will be equivalent to a smaller cell with larger K points. And here is the dilemma, like to do quick calculations that are hard to interpret, or do long calculations which are easy to interpret.
You mean increasing the number of key points is equivalent to the chain length of the system?
Yes, right? Yes, yes.
Okay, interesting point.
And if currently you have about 250, the facilities would allow to redo maybe with 1,000 atoms, so make it 4 times longer, and then this subgap would decrease.
Okay, so from my learning process, this number of key points means then the number of repeat units, the number of periodic cells in that direction. For instance, when we have 16 key points, means we have 16 periodic cells repeated.
Not,
For instance, right?
Not. It's similar, but not quite. The key points for small system means that one allows charge density to travel with momentum, with different values of momentum, with different values of velocity. But if one increases simulation cell, it means that it will be coexisting waves with opposite velocity, which will produce standing wave, but equivalent to composed of this waves with overall net velocities. So it is not a quick thing to discuss, but such theorem does exist, and we can keep discussing it.
Okay, thank you for the comment. I will ask Fatima again, maybe to clarify more for me in future.
So, may I ask 2 questions?
I hope that I can answer.
And those are maybe not questions. Those are discussion points. Amir may please try to address as you see, and then maybe we will make another element of brainstorming, addressing it by different members of the different attendees. So, did you explore the change of the geometry upon injection of the charge? Or if you didn't, do you expect any modification of the geometry due to injection of the charge?
Very good question. I didn't directly check the geometry. You mean when increasing the charge, check the cell size? Or
No. Re-optimize and see if optimization with charge gives different geometry than optimization without charge.
Oh, it's a very interesting point. I didn't check yet, but for sure I will check the optimal geometry for these 2 models.
Okay, so it is question number 1, and let me ask, well, everyone is welcome to contribute opinion, but primarily if Aaron is on the link, Aaron, would you please comment on this change of geometry upon charge and how to think with right terminology and how to interpret this possible phenomena?
Based on his orbital analysis in the previous slide, it looks like whatever the functional groups are that have the oxygens, since oxygen's the most electronegative, like negative charge is going to locate in that region, or it's going to be more dense there. So when you add more charge, it might localize further in that region.
Okay.
And then since there's more charge there, the nuclei will reorganize more in those regions. So that's my hypothesis.
Thank you. Can you also summarize your research of last year and a half in maybe 1 or 2 sentences? Like which advanced word one is using when electronic properties are changed and nuclear distances changed due to charge injection? Which physical effects can be following out of such injection?
So in the literature, people refer to these as polarons. So it's basically an electron or a hole which just interacts with the ions around it strongly. So it self-traps. are localized as more in certain regions of the molecule or solid. And I've been doing these calculations for like a year, I guess, so. But in my model, it's not, like it's fairly small, so it's hard to see the localization. But with the polymer, if it's long enough, you might see more, instead of the homo or lumo being delocalized fully, it might just be in a certain region of your polymer.
Mm-hmm. And is it natural to expect a redshift of absorption, or maybe drastic?
Yeah.
Okay.
So yeah, so your homo lumo gap, like in the figure that's shown here, that's like the distance between the peaks is 0.3 eV. So that will show up as like infrared absorption.
Okay, very good, very good. So it makes sense qualitatively, right?
Mm-hmm.
Yep. And please use this opportunity and maybe share a preprint of your work with Amir, or if you want, with everyone as a reference point, if Amir is interested.
Sure, it's my pleasure. I would appreciate that if Aaron shared it.
Okay, yeah, thank you, Aaron. And question number 2 on this slide. So this injection of the charge, how would it affect the conductivity of the material? Would it be more conductive or less conductive?
So with the charge injection, for sure, we expect to have a more conductive system.
Mm-hmm. Good.
So first, the gap is disappeared according to the homo and lumo of the new system, of the injected system. But again, I'm worried about this gap. I don't know how it affects the conductivity or no. But at least by checking the, for instance, the transition energy from the absorption spectrum, and also checking the time gap, we expect to have more conductivity compared to the original neutral model.
Okay, yeah, it sounds really great. And what could be the quantitative measure of absorption? Oh, sorry, not absorption. Quantitative measure of conductivity. Like we qualitatively we are telling gap is smaller, system is more conductive. But is there a way to convert this discussion into numbers?
So we can talk about the transition energy.
Okay.
And I would appreciate that if other audience give a comment on this. I'm not sure which kind of calculation we can
okay.
Give us more numerical analysis on this.
So anyone is welcome to contribute an opinion how to convert this discussion about conductivity into more quantitative way. And especially a comment from Dr. Han, from Yulun, would be appreciated here.
Roughly, you can just calculate the absorbance spectrum at zero energy. It will just tell you the conductivity of your system.
Okay, but but I agree with you that there is a theorem telling that absorption at zero transition energy would correspond to conductivity. But in the spectra that we are looking at, absorption at zero energy is zero. Is it just effect of human eye weakness? Is there a way to analyze it in a better fashion? like if we see that absorption is let's see, it's slide number 26, and on slide number 27 the absorption at zero transition energy is zero. But is it truly zero, or it is just a glitch of human eye interpretation?
Yes, probably you can adjust the light width for the absorption spectrum. So maybe you can just artificially increase this value.
Okay, and right now Amir is looking at this spectrum in the linear Y range. But if one would like to inspect the low values of absorption to focus on it, is there any other tools, any other approaches?
Like it's a log scale.
Oh yes, yes. Thank you. I think it would be really great. So if one would just modify Y range in the log scale, then things that look like zero for human eye will be, it will be not zero, but like 10 to the minus 2, 10 to the minus 4, and with and without injected charge, it will be different. It will be different value of absorption, and one can get orders of magnitude difference. Yeah, many thanks. Thank you to Yvonne, thank you to Fatima. And we have a text comment that Sarah needs to leave the meeting because of a class. Thank you for being with us for this time. Okay, many thanks to Amir, Aaron, Yvonne, and Fatima for discussing this slide. Sorry for making this so long stop. Amir, please take the steering wheel and
sure.
continue. Yes.
So the number, step number 2 was increasing the number of electrons. So for number 3, we want to check the decreasing the number of electrons. So make the ionic system. So we decrease the number of electrons. Actually, we subtract 2 of electron in foil. So again, that you can see there is a gap around 0.3 in between one low, but actually no, we cannot call it again a gap in the system. Similar to the previous one, for the original one LUMO of the system, there is a sub gap again. And if we, comparing to the previous step, we inject electrons. So, but here we subtract 2 electrons.
Or inject a hole.
Inject hole, exactly. Both situation increase the conductivity if we just take a look at the band gap between the occupied and unoccupied orbital. So this system, as Dr. Killen commented here, this catalionic system needs less energy to promote the electron from the HOMO to LUMO, from occupied to unoccupied system. And again, the transition energy and the wavelength of the system is provided for this model. Again, for BC, B to C, from HOMO to LUMO, the first gap is corresponding to the longest wavelength. And I would appreciate your comment here if you have a question or comment for the current model comparing to the step number 2 that we inject electron.
So any comments are welcome.
I guess the only comment I have is that it might be worthwhile to check doing these same procedure, but just with spin polarized calculations. Because in this case, it's adding or removing 2 charges.
Right.
But if you do spin polarized, that'll allow you to like simulate doing just the one at a time, which might raise less questions from a reviewer.
Okay, thank you for your comment. We have a spin polarization in the coming slides as well.
Oh, you're well prepared.
Okay.
Okay, if there are no more, and so the interpretation and analysis of the injected hole will be similar to interpretation and analysis of injected electron. So I think it's same style comments.
Okay, thank you, Dr. Kilin. For the next slide, I need Dr. Kilin and your help for the Fairway. So we said that from the absorption spectra, we can see which occupied and unoccupied pair of orbitals have more potential to be promoted. So here we set the Fairway in the incorporated promote the electron from HOMO to LUMO. And if you can see here, this is for real system. The electron of the HOMO are promoted to the LUMO. So so this time I have question, and I would appreciate others to answer my question. This is for my learning process. So first, what is the purpose of this promotion of electron? What are we looking for, and why we should do this? And after doing this, how should we treat or calculate the band gap? Band gap is between this, for instance, 313 to 314. This area should look for band gap, or no, band gap should be always in the original HOMO and LUMO number for the model. So I'm looking to get it from you.
Okay, yeah, Amir, thank you much for taking initiative and posing question. I'm very enthusiastic to answer it, but let's check if Yvonne wants to give a brief comment, because he is a developer of a unique method based on this promotion of electrons.
I guess typically your system is in the ground state, right? But actually, if you have some light or you have excess kinetic energy in your system, you can actually excite your system. So this kind of four-way control the electronic configuration. So in other words, we can compute the excited state for the system.
Okay, thank you. And the band gap should be big from the real HOMO and LUMO, right? For instance, here band gap is here in the left of this purple column, or in the right? I think in the left.
Original.
Okay.
Same numbers. So let me continue if I have your permission, and if you won't permits me to continue the idea. So thank you. The materials degrade with time, and one of the mechanisms for materials degradation is photodegradation. This is quite general and not unique, but especially if the material is designed, is already has response to photoexcitation, it will be degrading quicker under photoexcitation. So main thing in this section of the simulation is same as with pulverons that Aaron did explain. So if one promotes electron from HOMO to LUMO and optimizes geometry, the geometry will be very different. Maybe, well, depending on materials, it may be very different or slightly different. And if one practices photoexcitation, then relaxation, then photoexcitation again, the geometry will adjust following excitation, then following relaxation, and it will start moving and accumulate kinetic energy. And by accumulating kinetic energy, it will overcome the threshold of chemical stability and will break on pieces. So by looking a little bit further into this section, one can simulate the photo degradation of material. So one can go into molecular dynamics of decomposition of this polymer onto smaller fragments. Make sense?
Yes.
Okay. So you please take Amir, please take steering wheel and either ask questions or continue the presentations.
Your any question, you can go forward. Okay, let's go to the step number 5. As Aaron mentioned, we can also check the spin polarization of the system to regulate the momentum, angular momentum of the particles. So this is also, I'm curious about it. I hope somebody can interpret this because for me, I'm not good in this step as other steps as well. So I have also two questions again here. What is the purpose of this spin polarization and which range of this plot? This is just from the Gano plot I replotted MATLAB here. Which range of this plot we should incorporate into our results? For instance, I just zoom in into the previous plot in this new figure. And I don't know if you have some comments following by your previous comment. I would appreciate that if you can interpret or leave some comment here.
So if it was, so if we just did a singlet, like that red peak around -3 eV, that would move down to this empty spot in the spin down state. Does that make sense? But when you do triplet, you can kind of artificially tell VAST to do that fair weak command. Does that make sense?
Actually, I cannot leave comment here. I'm a little confused about this step and need to learn more and study more to be able to put some comments. And I could fill in if you can.
Okay.
What about
Aaron, may I contribute?
Yep.
Okay, thank you. So before going to these details about occupation of orbitals, the main thing, practical thing, would be to report total energy for ground state singlet without this modification, and then ground state triplet with this n up down. And if this total energy of singlet is less than total energy of triplet, then there is a high chance that this calculations was not necessary. But just in case, it is important to check whether triplet state will have more chemical stability than a singlet. Or it often happens that the triplet state is higher in energy than ground state, but lower than the lowest excitation, which will mean that system may absorb light, but will never emit, because any singlet excitation will convert into triplet and stop being optically active. So this spin flip processes may affect optoelectronic properties, especially in flexible soft materials. Let me share the screen really quick, and then you please take control back.
I should stop sharing or no?
No, it will. It should. I'll check if it will go automatically. It should go automatically. Okay.
Okay.
So if I'm just trying to give illustration and comment on the statement that Aaron did. So the peak here, red peak at -3, corresponds to former. So before we did modifications, it did correspond to LUMO. And the empty peak at -3.7, it was originally HOMO. By practicing this n up down command, one is taking population from HOMO with downspin and promoting it to the LUMO of upspin. And such configuration is very frequent in nature. So this modification of the electronic configuration is called triplet, and it often has different electronic and optical properties. So it is just good practice to check that the system doesn't make surprises for us and doesn't exhibit triplet properties. If it does not, it's good. It means easier for us computational chemists. But we need to do a fair job and check that this triplet configuration is not making surprises for us. You can take control back to
you can go forward. We can move on your system.
No, I'm done. Whatever I wanted to tell and to show. And the brief comment about the triplet states is that there is an experiment on demonstrational experiment. If one takes liquid oxygen and pours it on a magnet, it will be attracted to the magnet because molecular oxygen O2 is in a triplet state and it has magnetic properties because of unpaired spin. So it's presence of triplet states may lead to some additional features. Okay, sorry for a long comment. Please continue.
I appreciate your comments. Thank you very much. And the last step is to check if our cell size in the Z direction show the actually optimize the size, because usually in the nature, this is the concept behind DFT for the minimization. The system tends to be in the lowest energy. So as Dr. Chilin suggested, I check, I enlarge and also squeeze the cell size in the Z direction by interval of 0.1 angstrom. So the four systems are calculated, and for instance, plus Z direction, this is for zero tolerance, plus 2.1 plus 0.2. And both systems in bandium and also total energy show an increase in the value of the energy. So the current, actually the current the current cell size in the Z direction show the optimized one. Also, I further add more steps and add more value, for instance, minus 0.5 and plus 0.5 angstrom. So for minus 0.5, the system show minimum energy again, and not global minimum, but near to the Z tolerance value. So this raises the question if the current cell size is the short one, or if we decrease the system higher and squeeze it, it may be more near the optimized situation. I also check the system at the, you can see in the top the Z tolerance and minus 0.5 angstrom and plus 0.5 angstrom. The system, as Dr. Kennedy, you asked previously, no, the system is not decomposed, and but it's a little squeezed, and I just plug them together. This shadow red color show the 0 minus 0.5, and the natural color show the plus 0.5. And you can see that the system just squeezed, and we didn't observe any decomposition in the system. So I don't know how to support this data. If we can certainly 100% sure that this the current cell size in the Z direction is the best choice for the current model, or no, we need to have further investigation in this model. I appreciate your comments, Dr. Kirin, Taiwan, Dr. Bond, all other audience.
Thank you, Amir. So the polymer and any material in the limit of small elongations or contractions is expected to obey Hooke's law, to be harmonic.
Right.
So total energy is expected to grow if we elongate and if you contract.
Right.
And in this sense, your results are very correct, promising, and nice. You are but it looks like the step of this elongation and contraction is taken too large, because this blue line in the vicinity of the equilibrium is expected to be a smooth parabola.
Right.
So it means that maybe one may try to use step size like 10 times smaller, 0.01 angstrom plus 0.01 minus 0.01, and then it will draw nice parabola in the vicinity of the equilibrium.
I get your point. I actually set some more simulation. They are in pending status yet, but for sure I will add such a data point too. I also checked, as you mentioned, both systems show a parabolic actually energy surface for different tolerance. But yeah, I will try the smaller interval for this system.
So for your question about going beyond ranges and making hyper-extended or hyper-contracted system, right now the strand is surrounded by vacuum, and it is clear so that one can squeeze it further and further until when it breaks completely on conjugation length, and it will just create a dense, realistically dense matter. So if you keep contracting, the total energy is expected if you contract it not by small values but drastically, like 0.5, 1 angstrom, 10 angstrom. Total energy could decrease, but then material will lose its specific properties. At some point, if you keep squeezing it, it will be not this polymeric material. Its gap will be very different. Its absorption will be very different. So it will be just different material.
Right, because there would be some pre-stressed maybe ported in the system. I got you.
Yes, so it is also interesting research, but maybe it's not the first priority. To make sure that current research is fine, it is enough to check that equilibrium length was chosen correctly, and it seems that your calculation already proved it. So it's
okay. Thank you. Okay, the user size were the last one. I just didn't do your comment. Sorry for the key points as you discussed today. Also, I forget, sorry, to put the energy of the whole system. I will add the results and share with you, and also you can share with others to have a better understanding, better judgment before the different systems that we consider here.
So, Amir, if this is the last or slide, may
okay.
So you have yeah. May I ask you to make a favor and do verbal conclusions, and maybe if you didn't prepare them ahead, you may address like 3-4 questions, like which results are needed for practical applications, which results of your calculations can be compared to experiment, what you judge as a main finding of your work, and maybe connecting between first and last, what is the impact of your calculations onto engineering, fabrication, and utilization of these materials?
So, thank you for your question. Yeah, I didn't put the conclusion, just wanted to review the results and give some comments, receive some comments. So, first, for the band gap, we compare our results to the experiment. For instance, 0.9 is the initial result, and after using hybriding function, we get the band gap near the experimental results. So, this makes clear some optical electrical properties that may be useful for the industry. And sorry, I forget almost all questions follow the same target. Anything else that I can add? From our previous paper, actually before doing this class, I was interested in if we increase the circle length or length of the alkyl group, how they will influence the optical properties. But at least from the current results, maybe this is a completely clear result for you, but for me that was interesting to connect the current optical electrical results to the previous mechanical result of this polymer. And yeah, and I appreciate your comments if you can give me some feedback how we can improve the results or how we can better illustrate them, discuss them.
Okay, let me invite everyone to join me in thanking Amir for interesting and inspiring presentation. And probably it would be reasonable to open floor for additional discussion if there are more questions or comments.
Yeah, hi. Hi, Dr. Kim.
Yes.
I think, yeah, the 4 comments you provided in the end, I think that is very important. So, Amir, you should always have the mindset to think about, what's the major impact of this work, right? What's the major contribution you can make to this community, right? And what is the benefit of this work, right? For the not only the computation field, but also the practical engineering or material science field, okay? And also you should also think about what's the unsolved problem, which can be solved potentially in the future, right? Or in other words, what is the future next step we want to do along this line, right? You should always, have this mindset. So this will help for you to, draft the story, put figure and everything together, right? Make an insightful, deeper discussion.
Okay. So, Dr. Killian, you think these results are enough for initial draft, or we need to go further and improve the results, besides the comment that you put through this presentation?
It is, I'm open for any suggestions, but in order to, since human life is not very long, I think it would be reasonable to start putting draft together, and let me throw in a suggestion of combining figures, which you may update as we go, but combining figures in more like paper style format, with making several lines per panel. Like if you have several modifications of spectrum, you can show them not one line per panel, but several lines to have them condensed. If you have several homogeneous results of the same nature, like several density of states, you can put them in one multi-panel figure.
Okay.
And for each figure, try to compose detailed caption. So do not hesitate to make long caption explaining, like for 1/3 of a page, what is shown on the given figure. Professor Xia, what do you think about this plan?
Yeah, I think yeah, those are I think those are good for putting together all the results, summarize all the results in a coherent and organized way. So that is definitely very necessary for writing a paper if you want to submit and publish a paper. So, but I think before doing that, you should have in your mind you should have a story outline, right? What is the major motivation, right? Why you want to do this work, and what is the main conclusion you can draw, right? So I think for this study, if I understand correctly, so we want to understand, especially if we add, I think the first part is more about basic categorization and calculation, right, of the electronic property of this model, right? But the second part, I think that would be maybe the highlight part. You add electron, right? You add hole, and to look at their conductivity, right? Conductive behavior. So those are I think the key points you want to highlight. So think about that. Want to arrange the figure. Before doing that, you want to make a general storyline.
Okay. And Dr. Killian, can you also please give me your feedback? What's your opinion about the purpose of this study and highlight points?
I think the summary of Professor Xia is really good, is outstanding, and it summarizes most interesting finding. And if one arranges all materials as effort towards exploration, right now we are not in the quantitative regime, but qualitatively we predict change of the conductivity upon injection of the charge. And if we formulate the whole story as this goal, it will be better arranged. So each figure and each sentence in the future paper can be judged whether it brings us to this goal or not.
Okay.
So just following up on that, Liam, based on the calculations you've already done, one quick calculation is if you take your models where you inject charge, either electron or hole, and then do K-point sampling and see if the curvature of the bands change. Because it's expected if polarons do form, the effective mass should be heavier compared to without the charge. So that would tie into the overall goal of charge transport in these materials.
Yeah.
Thank you for coming.
Thank you, Aaron.
I will try to do that.
Okay. Are there more questions or discussion points? If no,
So,
please, David.
so I just have a comment from the discussion on the nitrogen subunit that we were talking about earlier.
Uh-huh.
So one of the slides had a paper reference, and I just looked it up quick, and it gives the name of that. It's a pyrrole subunit.
Pyrrole.
Not a pure.
Okay.
If you look at the chat, I just gave what the term that paper used for it and a systematic name that I just did a quick internet search to find.
Okay, thank you. Peter link. Okay, thank you, David.
So pyrrole. Oh, I see. Pyrrole ring with double R. D keto pyrrole systematic name. Okay, excellent. Many thanks. Many thanks, David. That's great. So if any of the attendees of the meeting were making notes with critical comments, please consider to send them directly to the presenter, to Amir. It could be useful, and we may not schedule exact date, but let's keep a plan on making arrangements and try to continue this practice of collaborative group meetings, maybe once per month or something like that, if Professor Xia is approving.
Yeah. Yeah, we should definitely do that. I think this is going to be a starting point, and in the future, once we have once we move forward, right, and get deeper, and we will have more collaboration. So this could be just one starting point, but I believe we'll have multiple work coming together in the future. So maybe let's make a plan later this summer, or maybe have another discussion, and then once we get into the fall semester, we can make a regular joint meeting.
Yep, it's a good idea. So we are close to completing today's plan. So for next week there will be another collaborative meeting on nickel catalysts, and in 2 weeks there will be a presentation by David on layered perovskites. So let me thank Professor Xia and your group for a very inspiring discussion. Thank you, Amir, for dedication, and all attendees for very valuable and deep thoughts and comments. So many thanks.
Yeah, thank you for organizing this meeting. It's very insightful and helpful.
Thank you for warm words.
Yeah. Okay. Have a great day.
Oh, you too. Thank you. So meeting is over. Everyone is welcome to disconnect.
Okay, Dr. Ken, if you have time, I need 5 or 10 minutes of your time for a personal meeting. I would appreciate that.
Well, I'll stay online and answer any questions if needed. But formal part of the meeting is done. If you need to depart, feel free. If you need to talk, I'll stay here until the connection is formally disconnected.
So, Dr. Ken, first for HSE06, you put NSW, ionic SW equals 0, right?
Yes.
So what if increase the ionic SW for that purpose?
It will start optimizing geometry under this functional. So any change in the way how electronic structure is calculated has potential to modify geometry. If we just change functional and do not inject electron or excite electron, then it shouldn't change geometry substantially. but even if it will be small modification of geometry, it is known that hybrid functionals are about 40-100 times more expensive. So it will be, unless we have a serious motivation to do it, we would like to avoid unnecessary expenditure of resources.
Okay, guys. Thank you.
Any other questions?
I'm good.
Okay. If there will be more questions, feel free to send email or request a Skype meeting. I will be happy to contribute.
Basically, could we have a Skype meeting around 5 minutes after this meeting? Are you available? You have time?
I do not know how long because there could be more questions from other attendees. So let's exchange emails and schedule meeting if you want to talk one to one. I cannot promise exactly in 5 or in 15 minutes. Let's schedule it by email.
Okay, sure.
So Raufan? How are you?
Okay.
How are you?
Good. How are you?
Doing good. Thank you. So how?
Very nice work, Amir.
Thank you.
Yep. Raufan, do you have any questions or comments?
Not yet. Not yet.
Yep. What you did in class was great. It's just not as close to my heart because there are no much electronic properties. It was only mechanical. So you did great job, but I'm quite attracted to project by Amir because it has this electronic and optical component.
Oh yeah, that's fun. It's good.
Okay.
Basically, will you record or upload this session?
If I have your permission to disclose.
Oh, sure.
Okay.
That's appreciate it. Very good resource. I always use your channel videos.
Okay.
Excellent.
Yeah, thank you.
Thank you.
Okay, basically, I will send you an email. Thank you very much for your time. I appreciate your effort.
Thank you.
Thank you also for Fatima. She helped me a lot. Also, I hope you can support me for the coming revision and for the work. Everybody else.
Thank you.
Have a good day. Bye. Thank you, David, for the comment on the Hyrule or Hyrule?
Hero.
Tyrol.
Hero. Thank you very much. Have a good day.
At least that's what the internet tells me.
Good.
Okay. Thank you very much. Bye.
Fatima, how things are going for you?
I need your help, but you did not respond.
Oh, sorry. If I please resend me correspondence because I always hope that my life will be easier, but it doesn't get easier. It's always some deadlines.
I don't know. I send you whatever I did, but I'm stuck.
Please just resend so that I see it fresher, and I'll put like skip all other things and focus on your project. Please just resend as a reminder, and I'll focus. Maybe I'll assign tomorrow Wednesday morning to go over it in details.
Oh, okay.
And
okay, the thing is like I can get the curve for energy, and eigenstep. And for magnetic field DOS, I cannot get the DOS for more than 0 magnetic field. I
Okay.
can get 0, but not. There is a problem on some. It cannot detect the higher than 0 value of magnetic field.
Okay, I'll check it. It probably means that I need to run the code myself and check what is going on.
And I don't know how to calculate the absorption spectrum.
Maybe
There is no-
maybe we can skip absorption spectrum for the next paper. Like we do not need
That
to.
would be great.
It will, yeah.
So I need to skip that theoretical part as well, right?
Huh?
For there is a couple of lines for absorption spectrum.
Do not erase them. Do not erase them now. If you decide to erase, I will do it myself.
Okay.
Keep them.
Okay, sounds good. Thank
Okay.
you.
Yeah, thank you.
Have a good day.
Bye. David, how things are going for you?
Going okay. So I was looking at the